Lesson 70, properties of limits and some special limits. We're going to run through these first several limits properties pretty quickly because we've used them before and are familiar with them. And then we'll take a look at the sixth and seventh one and kind of talk through them a little bit. Then we'll do some examples and talk about these special limits that are mentioned up here in the title. So properties of limits, 1 and 2. The limit of a sum or a difference of two functions is the same as the sum or difference of the limits of the individual functions. So you can take the limit of the sum, like add the things together first and then take the limit, or you could just take the limits of each part of that sum and then add those together. Similarly, the limit of a product or quotient, as long as the quotient doesn't have a denominator of 0. So the limit of the product or quotient of the two functions is the same as the product or quotient of the limits of the individual functions. So there's not like a product rule or a quotient rule. You can just do the limit of the top over the limit of the bottom if you're talking about a quotient. And then the pinch, so there's a lot of different names for this one, pinch or squeeze or sandwich theorem. Basically says, so g of x is always less than or equal to f of x and greater than or equal to f of x, or less than or equal to h of x. And if the limit of as x approaches a of f of x, the lower one, is equal to c, and the limit as x approaches a of the upper one, h of x equal to c, then it has to be true, or it's forced to be true, that the limit as x approaches a of that middle one must also equal c. You can try to draw a little graph in here to demonstrate this. So if we have a graph and f of x is saying it's the lowest, so it might be some graph down here. So that's in blue. And it says g of x or h of x is the highest. We'll do this one in red. It's always greater than or equal to. And then let's go ahead and look at and g of x, so f of x is blue, h of x is red. If we have g of x here is always greater than f of x, greater than or equal to, less than or equal to h of x. As we look at this spot here, as x approaches a, so let's call that value a. This x value is a. Since the lower one approaches some value of c, and the upper one approaches some value of c, that middle one, the one in the middle, it's sandwiched or squeezed or pinched between the other two, it also has to equal c. And then this last one, limit of a composite function, kind of worded a little bit differently, but basically it's saying if the limit as x approaches a of g of x equals something, so it exists, and the limit as x approaches that value of f of x equals f of L, then you can just do this all in one big thing. The limit of x approaches as x approaches a of f of g of x, so that's f composite g, simply equals the limit of the inside, and then you can plug that into the function of f, and that will equal f of L. There's a lot going on there, but it's not too hard to apply. You can evaluate the limit of the composite function by doing the inner one first to make sure it exists, and then plug that value into the outer function. So take the limit of the inner function, make sure it exists, and whatever that value is, put it into the outer function. So here's a few examples where we might see these things applied. Let the limit as x approaches 2 of f of x be 3. Limit as x approaches 2 of g of x equals 0. We want to find this limit. It will probably take me longer to write out than to actually do a problem like this. So by those first 5 rules about sums and differences in products and quotients, we don't have to add all these things together. We can actually take the limit of these individual parts. So the limit of, here's a product here, the limit as x approaches 2 of 2. Again, I'm going to write all this out just so you see what's going on here. Times the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. This is what it would equal because we can separate out the products and the sum. Well, it tells us a few things. Well, we know the limit as x approaches 2 of 2 is just 2 because the value is just 2. It doesn't matter what x approaches, it's just saying it's 2. Times this value here, well, up here it tells us the limit as x approaches 2 of f of x is equal to 3, so times 3, plus the limit as x approaches 2 of g of x is 0, so plus 0. So this just equals 6. Here's a couple things we need to be aware of. As we go through these next examples, if the limit as x approaches a of f of x equals L, does it have to be true that f of a exists? So just because the limit of a function is equal to L, can we say that there is an f of a? Well, the answer is going to be no there. If this were a continuous function, it would work. But it doesn't say anything about being continuous, so we can't say that. Because we could say, well, here's a function. It's a strange function, but the limit as x approaches a here exists, but there's an open circle here, so nothing exists at f of a. So you be careful about generalizations like this, especially if it doesn't say that the function's continuous. Is the following statement true? Why or why not? If x approaches, as x approaches 3, the limit as x approaches 3 of f of x equals L, then f of 3 is L. Well, no, that's what we just talked about. It doesn't state it's continuous, or it doesn't specify. So these would work for a continuous function. All right, if f of x is a function so that negative x squared is always less than or equal to f of x, which is always less than or equal to x squared, for all values of x, what is the limit as x approaches 0 of f of x? So we have two functions. We have, we have negative x squared, which looks like this, something like that. It's a little somewhat rough. And then we have x squared, which is a parabola this way. And then we have some function that is always greater than x squared, or negative x squared, so it's always greater than this, but less than red, or the x squared. And so it doesn't matter what's going on there. What has to happen is that the limit as x approaches 0 has to be equal to 0, because these two, the limits of both of these are 0, so it has to be in between there. And so that's using that pinch theorem or squeeze theorem. Next example here, this has to do with the composite idea. We're taking the limit as x approaches pi over 4 of the natural log of tangent of x. Excuse me. Well, we could say, let's just try to plug this in and see if it works, and that's what we do want to do. And we can check what's the tangent of pi over 4. Tangent of pi over 4 is equal to 1. It's continuous at 1, so we're okay with that. And so now we can just take the natural log of 1. Is 1 part of the domain of natural log? Yes, it is. So therefore, we know this is equal to 0. Natural log of 1 is equal to 0. And so what we do is make sure this works in here first, and make sure whatever the answer is part of the domain of natural log, and so they are, so we can go ahead and just plug that in and figure it out. The last part of this lesson just mentions, oops, I messed up here, this should say well-behaved. Most functions we work with are called well-behaved. There's two well-known functions that are not well-behaved at a certain point, and it is y equals the absolute value of x over x. As you think about this, absolute value of x, if you have a positive number, the absolute value of x is a positive number over a positive number. So you have a number over itself, so you'll always get 1. And then on the other side, if you had a negative, if you put negative values in for x, well, the absolute value of a negative is a positive on top, but a negative on bottom, so you'll have negative 1 because you'll have like a positive 7 over a negative 7. So we have this function here, and as we look at it, we realize it's not well behaved because the limit as x approaches 0 of this absolute value of x over x does not exist. We look at the left-hand limit, it approaches negative 1. The right-hand limit approaches 1. They're not equal to each other, so it doesn't exist. This next, so be familiar with that the limit doesn't exist at 0. Similarly down here, looks like we're having trouble as x gets closer and closer to 0. What happens here is this is a signed function, and it keeps oscillating up and down, but the period keeps getting smaller and smaller, if you can think of it that way, because as x gets close to 0, these numbers are changing very quickly. So we have a lot of oscillating that gets closer and closer in there. So we can say the same idea, the limit as x approaches 0 of this sine of 1 over x also does not exist. So these are functions that are what we say not well behaved. So be aware of those two functions. You'll see them a little bit later on.